Yeah. So, what is the equation? What is Coulomb's law? The equation for Coulomb's law.
F equals AE times the charge 1 charge 2 divided by the distance squared or charge squared.
Yes. And the name of this is Coulomb's law. What is this law related to? What is it very similar to?
The gravity, the gravity
Law of universal gravity. So it's very similar to the law of universal gravity. What is a test point or test charge?
No, it's always considered positive.
So it's a usually, unless mentioned otherwise, a positive charge. It's an imaginary, infinitesimally small positive charge that we use to talk about the field. What is the electrical field?
I don't have to explain.
So, even though the electrical field isn't a force, you can define the electrical field as you can define the electric field as being a electrical force acting on a test charge divided by the charge of the test charge. Get rid of the value of the charge. So basically, E is equal to the force divided by the charge. Or another way, force is equal to QE. It's a weird definition. So what would happen if I have two charges, Q1 and Q2? They're arbitrary. They're going to exert a force on each other. We don't know what direction the force is. And let's say they're at some distance D. What would, so here's the forces. These two forces would be equal, right? Newton's third law. What would happen if I half the distance? What happened to force? Mm-mm. So if I double the R, or if I half the R, what would happen to the force? If I decrease the distance between charges, what happens to the force? It gets bigger. So what exactly would it be? So if I decrease R by half, what would it be? Mm-mm. The R is being squared. This is an inverse square law. So what would it be? So remember my trick? Constants you just remove or you treat as one. We have a box, a box, a box, divided by a box squared. So I'm making this a half. And so this would equal 1 divided by a half squared. which would be 1/4, which would be 4 times. If you half the distance, the force quadruples. What would be if I double the distance? Same thing, except for now I would put a 2 on the bottom. So that would be 1/4. It'd be 1/4 as much. What would happen if I triple the distance? Again, it's an inverse square law. 1/3 it'd be 1/9 as strong. So the farther you get away, the very quickly how much it decreases. So let's say I have a positive and positive charge. What would be the strength of the field in the middle? Or equivalently, what would be the force on a small test charge Q? So what would be the strength of the field? 0. So using Coulomb's law, this charge, we have a little plus charge right here. So it'll have some force. And if this is the same, if these are, I should specify that these have to be the same value, then this would put an equal force. These two cancel each other out, so 0 force. What about a positive and a negative? And assuming they're equal but opposite charges. What would be the still to the strength here compared to if you only had one charge? So if we have this scenario, I have a force F. And if I have just this scenario, it would be attractive force, because I assume this is positive and that's negative. And thus, if I combine the two, 2F. So put the point in between be twice as strong as just having just one charge. What's an electrical field line?
It's like the positive and the arrow pointing away.
So pointing away.
The negative is
So these arrows are represented by putting infinite number of charge lines. What's some facts about this? So are they all parallel? Are they all straight lines? Are they always straight lines? Good. So if they put like 2 of them, then you'd see them curving and they're not always parallel. I just turned the heat off. What are the units for electrical force? What was the question? What I ask?
what is the units
For what?
of electric force?
And what are the units for electric force? Newtons. What about electric field?
Does that make you long? Or was it?
So what's the equation for electrical field? Electrical field is equal to what?
The charge times the force divided by the charge.
What's the charge of force? I mean, what's the units of force? What's the units for charge? Coulomb. So it's newtons per coulomb. And the units for electrical charge? Coulombs. So even though you shouldn't use the plus or minus sign in the equation, you should specify the charge as being positive or negative. So if we have a charge that has a strength of -1 microcoulombs, and it exerts a repulsive force on this particle here, meaning it's going to push it away, is this going to be positive or negative? Is the charge Q right here positive or negative? So if this is a negative charge, then this has to be negative too because it's repulsive. Going back to the previous, what would happen if I double one of the charges? So I have a charge Q here, a charge Q2, and let's say that they have a force F between them. What would happen to F if I turn this into 2? I multiply it by 2. Turn it into 2 times Q1. What happens to the force? But how strong would it increase to? It would double. So if I double this value right here, the force will get twice as strong. Again, you can put boxes everywhere. If you don't change it, just put in 1s. But if I double this, then my force is going to be twice as strong. If I have a point here and a point here, let's make this positive and this negative. Then right here, what direction will the vector be in? So we're assuming our test point is positive. So to positive, it'll be a straight line coming out. This is attractive, so it'd point toward it. And we add these vectors together, assuming they're the same charge, by drawing a parallelogram. And the new force will point in this direction. So down and to the right. What would happen if it was 2 positive forces in the same scenario? Well, again, this is going to be repulsive, so it point in this direction. This would be repulsive, so it point in that direction. Drawing my parallelogram. My force would be, you would try to go away from both of them. So my force would be going in that direction. So let's say I have a positive charge and a negative charge. What would happen if I double this charge and triple this charge? What would happen to the force? Increase by how much? 6 times. Good, you're getting the hang of it. If 2 charges repel each other, are the charges positive or negative? Are opposite. So you can't tell if they're both positive or both negative. All you know is they're the same charge. So if charge A repels charge B, you don't know if B is negative or positive. You just know that they are the same as A. What about this scenario? Let's say that A repels C and B repels C. What do you know about A and B? Still the same charge. Let's say I have two charges. A positive charge and a negative charge. And let's say I have an infinite number of them. I have a box. I want to add charges to this box and make them neutral. How would I make this box neutral?
Add the same amount of
positive, negative charges, yes. Little intuition about that. So when you create a positive charge and put it next to a negative charge, these lines start bending like this. But we still have, basically on this side, a lot of lines going out. They are slightly curved. So it would be kind of like that, where they're slightly curved. If I were to continually keep adding lots and lots and lots of positive charges here, what happens is we get a very, very strong thing like this. Where only a very few lines actually make it out. If that makes sense. Which means almost all of these fillet lines are really coupled together. So when you zoom far enough away, you can't even see these very few lines that are able to escape. Technically, this would wrap around the universe and come back to this point. It's weird to think of it like that. So, electrical force is very similar to gravity. Gravitational force. What would electrical field be very similar to? Acceleration due to gravity. That's actually another name for acceleration due to gravity is gravitational field strength. And remember the electrical field is proportional to the force on a test charge and inversely proportional to the charge of that test charge. What is micro? What do you replace micro with? It's like 1 micrometer is what?
1 times 10 to the negative 30.
Yes. If I have a uniform build, make these all positive, make these all negative, then I will create a uniform build. And if I put a small negative charge here, which way would it go? Yes, it'll be attracted to the positive and repelled by the negative. What way is these arrows directed? They're directed to, downward, or from up to down. So they go from up to down. There's a lot of problems having you find the force. I do use like electrons and protons. So a proton has a charge, and this number's on the test, of 1.6 times 10 to the negative 19 coulombs. An electron has a charge of 1.6 times 10 to the negative 19 coulombs, except for it's negative. That number and Ke is on the test. So if we have two parallel plates to where, so this is positive, this is negative, we're hooking it up to a battery. You'll learn that this is the symbol of the battery later. Battery has a voltage of V, and these plates are separated by a distance D. Then the electrical field, assuming that this is large enough that you're not near the edges, then the electrical field inside of it would have would be equal to the voltage difference divided by the distance D. This is for energy, we don't need that. Oh, this is going to get confusing. So we have C for coulombs, but we have C for capacitance. So one's a unit, one's a variable. We don't really need to compare about capacitance yet. But electrical field, this is a way if you wanted to create an electrical field, a strong one that you can actually work with. So definition of voltage is the work per charge. Work is equal to force times distance. Thus, the voltage would be equal to the field strength. So F divided by Q is E. We haven't learned about voltage. Voltage is work divided by charge, and basically working backwards, we see that E is F over Q. And it's just definitions. Units of voltage is volts. I bring this up because here's a problem. Let's suppose I have parallel plates separated by a distance. Let's make it 2 centimeters. I hook it up to a 9-volt battery. Let's go all out. Let's use a car battery, 12 volts. And then I put inside of it a small little metal pellet that has a charge of 20 microcoulombs. So I have some static electricity and charged it up. And let's say it's big enough that we can assume the field is uniform throughout this. How fast, ignoring gravity, you can use gravity later, but let's ignore gravity. How fast would this accelerate due to the charge of the plates? So first we need to calculate the field strength. Field strength would be equal to the 12 volts divided by 2 times 10 to the negative 2 meters. So that would give us 600 newtons per coulomb is the field strength. And let's say that this has a mass of 1 milligram. A little tiny speck. Then the force on it, would be equal to Q times the field strength. So that would be 20 times 10 to the negative 6 coulombs times our field strength of 600 newtons per coulomb. So we get a force of 0.012 newtons. And then F equals ma. Rearranging it, acceleration due to the electrical force would be equal to F divided by m. Or force is 0.012 newtons. Or mass would be 1 times 10 to the negative 3 grams. However, that's the wrong unit to use. What do we always want our mass in? Kilograms. So how many kilograms is 1 milligram? So I know 1 milligram is equal to 1 times 10 to the negative 3 grams. I like doing dimensional analysis. So 1 milligram, I know there is 1,000 milligrams in 1 gram. And I know there are 1,000 grams in 1 kilogram. So milligrams divided by milligrams cancel each other out. Grams divided by grams cancel each other out. I'm left with kilograms. So 1 milligram is equal to 1 divided by 1,000 times 1,000. Which would be negative 6 kilograms. Or acceleration would thus be 12,000 meters per second squared. It would break the sound barrier instantly. as soon as you connected these terminals together, you'd see that little pebble immediately drop. You wouldn't even see it. It would be floating there if you're in outer space, and as soon as you connected it, it would disappear from your vision and instantly be touching the plate. 12,000 meters per second squared. If we could have that field strength and that charge and that mass, it would go across the. Let's see, what is the diameter of the Earth? Oh, well, no, that's just 12 kilometers. So 12 kilometers per second. So every second, it would be able to travel 12 kilometers. But, really, for electrical force, this was the only example I've done. What's really useful. It's the only thing we can do with, unless you're doing, electrical force is mostly done on, combined with magnetism. But this is the only electrical part that's useful. If you just want to use electric force without any magnetism, this is the only example I can think of, because most of all the other ones is in combination of magnetism. Give you a hint, the bonus is basically this problem. Any questions? Think you got it?